Okay, thank you. And there goes the timer. Uh, Thank you, Jamie, and the organizers for this opportunity. But I am not going to talk about our DNAm aging biomarkers ready for clinical trials. Rather, I am going to do Biomarkers of Aging challenge in 10 minutes or less. So before I start, let me actually do some conflicts of interest. I built a clock called Systems Age, which can measure aging in 11 different organs of your body from a single blood draw, including brain health, brain, heart, lungs, kidney, immune, so on and so forth. So I may or may not be biased. And it is one of the biomarkers that we are going to be including in this challenge that we do in 10 minutes. But with that, let's actually start our challenge. So our defining problem is that we want an ideal surrogate biomarker for aging clinical trials, right? I hope everyone knows that, why we need that, right? I think Jamie set that up problem very well. But just to reiterate this, this clinical sort of the surrogate endpoint needs to be prognostic and responsive, as Jamie pointed out really well. And so we have our two criteria in some ways to sort of translate an aging biomarker to clinical trial. Well, my mentor, Albert Higgins Chen, forced me to add another one called reliability. The reason why he forced me to add this was a very valid one, by the way. That is because if we need to have these biomarkers in clinical trials, they need to be reliable, or else you would require significantly more number of samples to actually run this clinical trial and get a significant effect size, or else you wouldn't be able to run this clinical trial with sort of hundreds of samples or maybe thousands of samples. So that's why you need sort of reliable biomarkers. If you want to know more about this, go check out his paper. Okay, so now we have our three criteria. Let's actually define a validation framework. For this, we built TranslAGE. This is a framework that can help us validate clinical biomarkers for surrogate endpoints. And this is agnostic of any type of biomarker, aging biomarker. So we could theoretically use this for proteomic biomarkers, metabolomic biomarkers, clinical biomarkers. We're going to use this for DNA methylation aging biomarkers today, but we could do it for any particular purpose. For the purposes of today, we're going to use this for prognostic on 21K individuals and 40 plus, 30 plus aging phenotypes, responsive around 51 different longitudinal longevity interventions, and reliable, we are going to look at technical reliability, but also something new, biological reliability. And we're going to talk about that as well. So now we have our framework. What are we going to test? We're going to look at 110 different aging biomarkers. Exciting, right? 110. So what are these biomarkers? These are the Gen 1 clocks, the chronological age predictors. And again, this slide has been inspired by a paper that Jamie wrote really excitingly in 2020. So we know that these Gen 1 clocks, these chronological age predictors were kind of prognostic. To improve that, we got the Gen 2 clocks, which were the mortality age predictors that were even more prognostic. They were not reliable, neither of them. To sort of solve that challenge, we essentially got the Gen reliable clocks, the PC GrimAge, the GrimAge V2, Dunedin pace to essentially solve this challenge. And more recently, we have had a burst of what I call the Gen explainable clocks, the system scores that I just mentioned, the causal clock that has been generated by Albert Ying, the different epigenetic proxies that have been generated by Omic MAge and Riccardo Marioni. All of these are really exciting clocks. Again, these two new generations are reliable, at least technically speaking, but we do not know anything about responsiveness across the board for all of them. So we have to answer these questions. With that, let's actually just make this a little smaller. I'm not going to talk about the Gen X clocks because there are too many of them. I'm going to focus on the Gen 1, Gen 2, and Gen R. If you want to talk more about this, you can come and talk to me by the poster. The poster is already down, so too late for that. If you didn't come, too bad. So let the games begin. So first validation, DNA methylation aging biomarkers are prognostic or not. And we're going to test that in diverse populations. So one of the challenges has been that typically we've tested these biomarkers in very Eurocentric Western populations. So we're really trying to test this in a very diverse cohort. We're trying to accumulate this in a wide variety of cohorts and bring together sort of very diverse ancestries and racial and ethnic backgrounds. We are also going to look at different aging phenotypes as well as look at different standardized metrics. One of the challenges, as you might have known about this, is that some of these metrics can be manipulated actually in the actual biomarkers of aging challenge, not this fake one that I'm trying to run here. Some people actually kind of try to hack the hazard ratio. So we now know that these metrics can actually be hacked. So we really want to think critically about which metrics we are using to quantify these measures. So for the simplicity of this analysis, I'm just going to show you one of these metrics, which is AUC. Why I choose AUC is actually after a conversation I had with the folks at ARPA-H. And this is because AUC is a really nice metric which we can really compare across a lot of different biomarkers that are out there. And there's actually an AUC analysis that you can do for time to event data as well, which is why we choose this. And you can see from this around 11K individual AUC analysis that somewhere around sort of Gen 2 plus clocks, we really started to get into what we call as the good AUC arena, sort of above 0.8 AUC. We are seeing around 0.83 AUC for our best GrimAge V2. So based on this, what does our leaderboard say? Okay, so our leaderboard says at this point that GrimAge V2, just based on prognosis, is the best. And I promise you, neither RK nor Steve paid me for this. So let's move on to our second validation. Are DNAm aging biomarkers responsive? And so the challenge we faced here was that there are a lot of sort of these small clinical trials that are out there that are being run to look at the sort of responsive, well, to see if DNAm aging biomarkers are being changed or not. But there is no kind of standardization in measuring which DNAm aging biomarkers they're really looking at. And that kind of keeps us guessing whether these biomarkers are really responsive or not. So to really solve that challenge, what we did was essentially accumulate all of this data. So we went to public repositories as well as private repositories, and we collated 51 longevity interventions and calculated 110 different DNA methylation aging biomarkers. And that landed us with sort of this whole big heat map. And each little box that you see in this heat map is the mean difference of scaled epigenetic age deviation pre and post this intervention. So essentially the effect size, right? Make sense to everyone? Cool. You can read more about this in our preprint, which we just published I think, last week. But what we did do with this now is, now that we have these 51 interventions, we put this all for each of these clocks that we have. And so each little dot that you see for all of these clocks is one intervention effect size, as you can see right here. And then we performed a very simple analysis, which was a one-way t-test. Simple, right? To check if this clock is essentially decreasing epigenetic age across the board for all of these 51 interventions. And what we see now is that only these kind of second generation reliable clocks, the PC PhenoAge, PC GrimAge, Systems Age, Dunedin Pace, those are the only clocks that are sort of significantly decreasing epigenetic age across the board, AKA they are responsive to these 51 longevity interventions. So we are really excited now to say in some ways that these clocks are responsive, especially these Gen 2 plus reliable clocks. Okay, so now how does the leaderboard look? Okay, drum roll. Okay, so behold, my clock shows up best. I promise this is no bias. Okay, guys, please, no bias here. But no, jokes apart, it's really close here, right? We can't really make much of a difference. So we really need to go to our third metric, which is reliability. So are DNAm aging biomarkers reliable? And we really need to ask this question because we have talked about technical reliability, which is just test, retest reliability. And we looked at about 196 individuals with 2 replicates in EPIC V1 array. But a new kind of reliability, which we are really thinking about, is biological reliability. When you really sort of take DNA methylation data from the same individual across different times of day with different variations such as meals, put them through stress, so on and so forth. Because this is critical. There could be variations between ages across the day, so on and so forth. And so we did this for 34 individuals with 8 replicates, again, in EPIC V1 data. And what we see is something really interesting, that a lot of these clocks are technically reliable, which you can see on the x-axis, but on the y-axis, they are mostly not biologically reliable, which is really interesting in my opinion. Only a handful of clocks show up to be biologically reliable. But I should point out that this challenge of biological reliability is not unique to DNA methylation. This exists across different biomarkers. And I will point this out in a minute. So the preprint for this would be coming soon. Okay, so the final leaderboard, what does it say? Any bets? Jamie, any thoughts? Okay, Jamie says PC Grimage. And she's right, actually. So PC Grimage does show up to be the best clock. But here's the thing, this is a very preliminary analysis. We do need to do a lot more analysis to really validate these findings. We need to improve TranslAGE as a framework, and I'll talk more about this in a second. But the more important point here is that we really need to understand the interactions that exist between these criteria. Because clearly, as you can see, I've done a correlation between these different criteria. There are some positive and negative effects between the correlations between these criteria. For example, look at prognosis and biological reliability, and that's concerning, right? As we optimize for prognosis, there seems to be a decrease in biological reliability, and we need to think about that. So what's our path ahead? I know I'm going into time ahead. Okay, so big important part is TranslAGE. We need to improve this framework itself. We need to think about diverse longitudinal cohorts, age stratified analysis, as Sarah mentioned yesterday. That was a really interesting thought-provoking talk. Responsiveness, again, we need more interventional studies and reliability, more biological reliability data sets. So lots to do here itself. Second, we need to improve our aging biomarkers on different criteria. As you can see, there's potential for improvement. And as I said, these challenges that I pointed out are not just true for DNA methylation aging biomarkers. I pulled up some biological reliability data for proteomic biomarkers and clinical biomarkers, and this stands valid for all kinds of biomarkers. ICCs are really bad for biological reliability for proteomic biomarkers as well as clinical biomarkers. So this is concerning across the board. And last of all, it's important to know that all of this analysis will not lead us to a surrogate biomarker. Only a short list of potential biomarkers that we would need to test in potentially a surrogate biomarker and clinical trial. So prognostic plus responsive does not equal surrogate. So what TranslAGE would really give you is provide a short list of biomarkers to test in a trial like that, right? Because you don't want to be doing sort of this multiple testing with 110 biomarkers in that particular trial. With that, I just want to thank the few of the many scientists who really provided their data and code that made this analysis possible. And this is a collaborative project. Sorry, Jamie, just wrapping it up. And I want people to kind of contribute to this. And yeah, that's the Higgins-Chen Lab, TranslAGE, Bigger, Better, Nobler. Thank you for all my collaborators. Thank you. Yes, yes, yes.
Okay, there is a minute on the clock if anyone has a question. Okay, I'm going to go 2 questions.
Thank you, stunning. Stunningly good, actually.
Yeah, thank you.
And I've got a question about your definition of biological reliability. Are you actually measuring biological differences that are real and therefore dismissing some clocks as not being reliable? So are you comparing blood taken at 8 a.m. on 2 separate weeks and saying if there's a difference, then the clock's not reliable?
Yes, so we are doing that like 1 week apart. And our assumption is that your biological age should not change within a week significantly. That's our assumption going into that analysis. Yes. Yeah, we can more than open to rethinking some of these assumptions that we have. So this is why we are putting this out there.
Lynn took my question. I just,
Yes.
I reemphasized the point. What is the ground truth in that situation?
Yes, and again, more happy to rethink this.
Okay, and that is time.
Thank
Right.
you.
Thank you.